So we said a black body radiation is the best radiation, right? And it's the largest amount of watts that can leave a surface, and that's sigma T to power 4. So E black 1, that's saying that what is the radiation leaving a black body at temperature T1, right? And so it's sigma T1 to power 4, right? Where sigma is the Stephen Boltzmann constant, and T1, that's the temperature in Fahrenheit, all right? So now if you would like to figure, basically if there is a surface 1 over here and surface 2, and you are trying to figure out how much is the heat transfer between the two of them. So you would say that this guy is watt per meter square. So let me multiply by area 1 to get the total watts leaving surface 1, right? If EB1, that's watt per meter square, we multiply by area 1 and that become watts, correct? Now, will all this watts leaving surface 1 end up going to surface 2? Not all of it, right? Only a fraction of it. What is that fraction? F12, the few factor. And again, there are table and chart that we will see to calculate that F12. But basically, out of all the A1, E black 1, only F12 will end up going to surface 2. At the same time, the story is also the same on the other side. That guy at T2 will radiate. The black body radiation is EB2, which is sigma T to power 4. All right? And this radiation per unit, this is watt per meter square. You multiply by area 2 and you get watts. Will all this watts leaving 2 end up going to 1? No, only a fraction. How much? F21. By definition, F21 is the fraction of radiation leaving 2 and going to 1. That's by definition. It's now the job of all those table and chart and equation to calculate that F12 for us correctly. But we will get it eventually, all right? So this guy is sending 100 watts to this guy, and the other one is sending 80 to the other. So at the end of the day, what is the net heat flux between the two of them? It's the 100 minus the 80. Right? So that's why the Q dot 1, 2, the net radiation between 1 and 2 is basically this minus this. All right? So we can actually say that it's going to be area 1 F12 sigma T1 to power 4 minus area 2 F21 sigma T to power 4. But A1 F12 is the same as area 2 F21. Remember the reciprocatory rule? So he pull it together, and he even pulled sigma together, and what does he finish with at the end? T1 to power 4 minus T2 to power 4. So the radiation between those two bodies is area 1 F12 multiplied by sigma, open the brackets, T1 to power 4 minus T2 to power 4. And that area 1 F12 can easily be replaced by A2 F21. Right? And if surface 1 is also surrounded by surface 3 and surface 4, he will get radiation not just from surface 2 but also from 3 to 4. Right? All the surfaces that he can see them will send radiation to him, and he will send radiation to them. So at the end of the day, the QI, any Q coming to any surface, would be the summation of the Q that he's exchanging with all the other guys that he can see them. Some of them will be plus, some of them will be minus, meaning that I could be, say there's a flame here near the door, so I'm getting radiation from him, I'm getting hotter, but because I'm closer to the frame, I'm hotter than everyone else in the room. So I will start radiating to everyone because they are lower than my temperature. Okay? So what is, at the end of the day, what's the Q that I'm getting by radiation? It will be the Q from the flame minus the Q to Jason, the Q to Lou, the Q to Jesse, and Q to everyone else in the room that I'm sending to them. All right? So that what complicate the convection, the radiation problem compared to convection and conduction. Because the conduction, we used to conduct only to the guy to the right and the guy to the left, right? And the convection, it was only between the surface and the air next to it. But in radiation, at the same moment, you could be radiating to everyone that you see, while you are also getting radiation from the hot source outside, that hot surface that you are also seeing, right? So the calculation become really very complicated. So we will limit our problems in this course to 3 body radiation. Although in real life, you can, on an Excel, easily you can solve a problem where you are radiating to 30 students in the classroom, and the room ceiling and the room floor and the room wall. That's not a problem. But for our homework and quizzes, we will just stick to 3 body radiation. So just the flame, me, and Jason, and that's it. Right? I'm getting radiation from the flame, I'm radiating to Jason, while Jason also seeing the flame and radiating to the flame and radiating to me. Alright? But know that it can be easily done on a computer. And if you find in the exam or the quiz 4 body radiation, like 4 bodies radiating, you better guess that there is a symmetry in the problem that can lump 2 of them together as 1 body. Right? You don't have to solve 4. I will never ask you to solve 4. Right? Just like that midterm exam, yes, there were 9 equations, 9 unknown, but I will never expect you to have a calculator that can solve 9 equations and 9 unknown. You bet there must be a symmetry that can turn the problem into just 3 equations, 3 unknown. Alright? So now let's see the radiosity and how will it solve this problem, how it will make the problem very similar to what we had earlier in the course when we would say the Q is just delta T over R. Here we'll say that the Q is 2 J's divided by the resistance between them. Alright? So what is the radiosity J again? It's what you send to the outside world. What you send is your radiation. You are not necessarily black body radiation, so you are not going to radiate sigma T to the power 4 only. You are going to radiate fraction of this. Epsilon sigma T to the power 4. If you are a black body, you will radiate sigma T black body 1 to the power 4. That's our way to say you are a black body radiation. But if you are not a black body, you will have sigma multiplied by epsilon multiplied by T to the power 4. Is that understood? So the diffusivity is what, it's basically what distinguishes you between you and black body. You are only radiating fraction of it. You have the temperature. You are at 1000 Kelvin, like the black body at 1000 Kelvin, but you will not radiate that much. Alright? So on top of this, you have rho G. And so Ji, your radiosity of surface I, is basically, you can see this, it's rho I Gi plus epsilon I E black body I. Alright? That's what go outside. Very good. Rho I, remember, if the surface is not transparent, there is no tau. Tau is 0 for opaque body. Right? We are talking about a piece of wood, a piece of steel, a piece of, not a piece of plastic, clear plastic, not a piece of glass. Radiation cannot go through it. So tau is 0. So that leave alpha and rho equal to 1. Right? There is nothing else. And also, we assume because it's gray body, we assume that epsilon is the same as alpha. So some surfaces don't have alpha equal to epsilon. Alright, for example, you know the solar heater, this black sheet, you know how does it look like, right? Solar heater? Does anyone? I see your eyes telling me that you haven't seen a solar heater before. So it's a black surface with bunch of pipes going through, and it basically getting all the solar radiation, getting hot, heating the water, so then the water basically goes into your house hot, right? Rather than using electric heater and pay a lot of electric bill, and we are in Tulsa, Oklahoma, where the sun kills us in the summer, you know, why don't we just let it heat our water, at least for the dishwasher? And right?
It's really killing us.
Right.
That's what I was thinking.
Yeah, it's really hot, right? I agree. Although we cannot complain the last few days. I mean, it's perfect summer.
I can.
Okay. I'm actually a little bit cold. But anyway, so this surface actually, it's really great that it has alpha really high because it's black. It will absorb like crazy. But it will also radiate like crazy. And so it could actually end up heating the tree nearby. All right? You don't want this. So they have special selective coating, special material that will make alpha really high, but make epsilon very small. And those would be and they will claim this, of course, in their brochure, and they will tell you, our solar heater can beat any other solar heater in competition because we use selective coating, where epsilon would be really small and alpha is really, really high. So we absorb, but we don't radiate. And so this guy gets hotter and hotter and hotter without losing radiation to outside. Okay? So without those special material, epsilon would be alpha. Okay? So in our problem, epsilon is alpha. All right. So now this rho I should be replaced by 1 minus alpha because tau is 0, and because alpha and rho and tau used to be 1. So if there's no tau, then rho and alpha just make 1. So here remove rho and he replaces it by 1 minus alpha, except that also alpha is epsilon, right? For a gray body, alpha is epsilon. So rho now is 1 minus epsilon. And so at the end, Ji is epsilon E black body radiation plus 1 minus epsilon Gi. All right? And a black body have epsilon equal 1. So J for a black body is, this is 1, and this will be 1 minus 1. So it basically be 1 minus 1, that's 0. So this guy will disappear. So basically tell you that a black body will not reflect anything. He will just break anything that's fall on a black body, get captured. Just like a black hole, right? So black hole basically absorb everything, even the light cannot leave because of the gravity field. That's the theory, at least, right? So a black body also will absorb all the radiation and nothing will get reflected. He will still radiate his own, but he will not reflect the radiation. Okay? So what if it's not a black body? Then it will reflect some, right? So here what happened when you are not a black body. So the Q leaving you for non-black body will end up being this. Okay, I'll show you the proof in a second. So Qi is AI epsilon I 1 minus epsilon I EBI minus GI. So graphically, how we can plot this, or how can we show this? So we can imagine that the surface will have ABI, and then he will send to the wall GI, and the difference between GI and ABI is this resistance, the surface resistance to radiation. So every surface that's not black body will have this surface resistance to radiation. If he was a black body, that resistance would be how much? 1 minus epsilon I would be 0. And if this resistance is 0, just like, when we used to neglect the conduction of a copper wall, and we used to say that resistance is 0, what this mean? In conduction, we used to say then this temperature is the same as that temperature because there is no resistance between them. Well, the same thing over here. If this was a black body, his radiosity will end up being his black body radiation. his GI will just be ABI. He will be sending to the whole world his sigma Ti to power 4. But because of his epsilon, because of his emissivity, because he doesn't have emissivity equal 1, he will have a surface resistance 1 minus epsilon over AI epsilon I. That is the surface resistance. I didn't prove why, but I will show you in a second why. But the point is, now we created that concept that in radiation, the surface will be sitting at E black radiation, and he will be sending his J1, and the Q that he will be sending would be his AB1 minus J1 divided by the resistance of the surface, where the resistance of the surface is 1 minus epsilon I over AI epsilon I. Okay? And so if you would like to find out how much radiation is leaving any surface, you just say AB1 minus J1 over the resistance. The resistance is just function of his property and his area. AB1 is function of his temperature, sigma T1 to power 4. J1, however, would be function of the outside world. It's the outside world that determine your radiosity too. Alright? Just like it's the heat transfer with the other surfaces that determine your temperature in conduction and convection. Your temperature is controlled, temperature of the wall would be determined by how much is the other guys are sending. Right? So now why is the surface resistance is basically this this 1 minus epsilon I over AI epsilon I. The proof is very easy actually. It's just this. What is QI? The net Q that's leaving you will be how much you are radiating, AGI, minus how much you are receiving. Remember, you are getting G from the world and you are sending J. So the net heat transfer by radiation, look at this. The world is sending J to you. The world is the other surface around you. And you are sending back J to them. So at the end of the day, if you are getting 100 watt per meter square and you are sending 80 watt per meter square, the difference is the net Q that will end up going, you'll be benefiting from. That is the net heat by radiation. You are going to use it to melt an ice in a tank. That's your quiz in a few minutes. Yeah, that's okay. We are running out of time. I have to get 10 quizzes before next Monday.
How many do we have?
We have 6 so far, so we still need 4. So
Let's leave it for
Just do it all next Monday.
I'll help you. So so you are getting G and you are sending J. The net difference between them is what you absorb. It's the net radiation that you will end up using to melt ice, using to heat something inside. Okay? So that's why QI is area I GI minus area I GI. Okay? And he's just substituted for GI from here. GI actually from the previous page. If you look at here, GI, you can bring it from JI minus epsilon I EBI divided by 1 minus epsilon. Basically, this equation, just put GI in one side, everything else on the other side. You will get exactly this. GI is GI minus epsilon EBI over 1 minus epsilon I. Okay? So again, Q is J minus G, and here is J and here is G. And so now he just pulled things together, and that's the relation that we have. And now it just filled exactly the model that we always look for, that Q is something minus something divided by something. That division is our resistance. The two things that we are subtracting, those are equivalent to the temperature in conduction and convection. Now it's the radiosity. All right? Does this make sense? So again, now when you have two bodies radiating to each other, you'll have ABI1, ABI2. You have the surface resistance of surface 1, which would be what? 1 minus epsilon over AI epsilon I, right? Just like this guy. This is the surface resistance. 1 minus epsilon over AI epsilon I. So 1 minus epsilon 1 over, say, A1 epsilon 1. And this guy, 1 minus epsilon 2 over A2 epsilon 2. What you get after that? You'll get J2 and you'll get J1. Right? So what divide or what separate the black body radiation from the actual surface radiosity, what will leave the surface, is the surface resistance radiation. And again, that number would be 0 for a black body, or epsilon if epsilon is 1. That term will disappear. Okay? Very good. So now this guy is sitting at J1, this guy is sitting at J2. How much will they radiate to each other? It's Jy minus J2 divided by the resistance between them. What is the resistance between them? It's very simple. It's 1 over A1 F12. Okay? So we have two kinds of resistance in those problems then. There is surface resistance to radiation and there is geometry resistance to radiation. It's the view factor part. It's basically how far the surface is, what angle you are seeing him. So that resistance depends on the F between the two bodies. And so this resistance between the two bodies can be 1 over A1 F12 or 1 over A2 F21. Okay? Same thing. A1 F12 is the same as A2 F21. And so how we are going to write the Q then? The Q eventually between 1 and 2 is going to be AB1 minus AB2 divided by all the resistance in the way. Surface resistance 1 plus geometry between the two of them plus surface resistance 2. And become just like all the conduction and convection problem that we had before. Alright? So here is the, I guess when you put it this way it's really complicated. So I would just say that Q1 to 2 is AB1 minus AB2 over the first resistance 1 minus epsilon 1 over area 1 epsilon 1. Actually, I don't have the push space. Plus 1 over A1. I cannot touch it. This is bad. Let me just open the page here for you. So AB1, AB2, J1, J2, and this is the 1 over the area 1 F12, and this one is the surface resistance. 1 minus epsilon 2, area 2 epsilon 2, and this guy is 1 minus epsilon 1, area 1 epsilon 1. Surface resistance, geometry, and surface resistance. And the Q dot is from 1 to 2. And so you can calculate Q dot 1 to 2, although maybe this guy is only at 100 Kelvin and this guy at say 400 Kelvin. And you know that the heat must be coming the other way. That's okay, just write the equation and the equation become negative. Alright? So Q12 in that direction, it's AB1 minus AB2 divided over all the resistance. R surface 1 plus R geometry plus R surface 2. Or basically this plus this plus this. Okay? Now the question is, what you should think about now is how we can calculate those F. This F12, how we can get it, right? And so to answer this, it's all geometry, and so that's why they did it for us, and they put it in all those tables. So let's look at some of those tables. For example, here. So this is two plates facing each other. So by the way, this radiation is only from the surface facing the second plate to the surface facing the first plate, meaning that each one of those plates have another surface too, and that other surface is probably in radiation with the other guys that he can see. So this is only the part that they are facing each other. So if you would like to get F12, all you need is the ratio L2 over D. So what's D? That's the separating distance, and L2, that's this length. So you get L2 over, let's say it's 2. You come over here, and you have to read L1 over D. And you read L1 over D, say it's 0.3. So you just come here and you say, well, F12 is 0.1. Okay? That is, so if the problem is two plates separated from a distance, and you are trying to calculate the Q between 1 to 2, you again would say Q dot 1 to 2 is EB1 minus EB2, and on those EB is again sigma T to 1 and sigma T. It's sigma T to power 4 basically. That's the black body radiation. Over, and you would say 1 minus epsilon, area epsilon, plus 1 over F area plus the other surface radiation. It's those three resistances: surface radiation, geometry radiation, and surface radiation. And the F will come from a chart like this. If it's two parallel plate, if the two plates are normal to each other, here is the other chart, and you get F12. Alright? All you need is L2 over W. You will read this number. Let's say it's 1. And you would read F12. What if you need F21? Excellent. Yes, the reciprocatory rule. Very good. Alright? Two disks, not two plates, but two disks facing each other. Same trick. Right? Two concentric cylinders. And so this is F21. So 2 is the outside surface, and 1 is the inside surface. Alright? Can anyone tell me what's F12? No, I want a number. I want you to say the number. What's F12? Anyone? It's the same. No? Think again. What is F12? What does it mean? What's the definition of F12? What is it in words? Like if you're explaining it to your 10 years old child, you would say what? F12 is the fraction of radiation leaving 1 going to 2. Now what is the fraction of radiation leaving 1 and going to 2? No. Think again. I just need a number. What is the fraction? 1. Excellent. Del is saying it's 1. Why? It's completely wrapped around. Everything leaving 1 will have to hit 2. So Del said F12 is 1. Well, how about F21? It's not 1, right? Why F21 is not 1?
Because it's radiating heat out.
No, it's not. So again, this is in all those plates. All those, say over here, for example, this is only that surface, the inner surface, or the two facing surfaces. We are not talking about the outer one. So in those two concentric cylinder, 2 is the inside of the outer cylinder, and 1 is the outside of the inner cylinder.
So it could be very deep back to itself.
Excellent. Excellent. So Brandon saying F21 was not 1. We see it's not 1, right? I mean, you can read F21 is all over the spectrum. Why it's not 1? Because there is F22. 2 can see itself, right? 2 can see itself. It can see itself. Radiation leaving it will hit itself. However, this problem, when I try to calculate the Q, I will still have AB1 and AB2 and 1 over F1, 1 area 1, F1, 2, and surface resistance here, 1 minus epsilon 1, area 1, epsilon 1, and 1 minus epsilon 2, area 2, and the Q leaving 1 going to 2 will just be this minus this over the distance. There will be no radiation. Q22 is 0. Q22 is 0, although F22 is not 0. Does this make sense? So why F22 is not 0? Because F can 2 can see itself. So the radiation leaving 2 can go and face the other part, right? But at the end, when you try calculating the Q, the watts that we will gain, the net heat transfer by radiation, it's 0. Imagine if I'm in flame, the flame is so strong, I start burning, and so my hands are in flame. This hand can see the other hand, right? But does this radiation, the flame coming here, going to the other hand, how much will this increase my temperature? 0, because all the watts that I'm sending from here will end up being gained here. So yes, I can see myself, help, right? But I cannot really give net heat to myself. So that outer cylinder too, yes, it can see itself and it can have F22, but Q22 is 0.
Why can 2 see itself, but 1 can see itself?
It's so again, I'm talking about the outer surface of 1. So I'm talking about this guy, the outer surface of 1, and when it comes to 2, I'm talking about the inner surface of 2. So the inner surface of 2, this part can see this part, and you can hear it. But 1 here cannot see.
I thought you meant by reflection off of the middle.
So if you are concerned that 1 can actually send to 2 and then he can send back again to 1, right? Yes, it can, but then it's once he sent to 2, it's not his radiation anymore. All right? Remember in the movie Independence Day when the aliens were transferring signal to each other by satellites? The countdown, because they cannot see each other. So basically the spaceship was here and the other spaceship that was trying to hit the other part of the world was on the other side. You haven't seen that movie? That's the best movie ever. That's the best movie ever created in the So the point is they couldn't communicate with each other, so they were using our own satellite because this Earth was blocking their view, right? So they have to basically use our own satellite to count for our destruction. And so it takes this engineer basically he managed to get the signal and realize they are counting, and there is no point trying to negotiate with them because this is actually the countdown for our destruction. Watch the movie, okay? All right. So to answer Mallory's question, which surface can see each other and which surface cannot? Let's go to this slide. So a plane surface like this, F11 is 0. He can never see itself. He cannot radiate to itself. Everything leaving him will go to the outside world. Something like this, that's exactly like the problem that the inner cylinder. Radiation leaving it cannot hit itself unless it bounces from something. But if it bounces from something, that radiation is from that something. It's not its own radiation anymore. But something like this, a concave surface, can see itself. And that's what happened with the outer cylinder, the inner surface of the outer cylinder. Something like this can radiate to itself. It can see itself, but the Q at the end of the day, of course, it's 0. Because even if he lose joules from this, he get them here. All right? So F12 is 1 because of that. Okay? All right, so that chart, if it's hard for you to read, you can use the equation. Ouch. You can read the equation, although the equation is actually a little bit long. But, right? So maybe the chart is okay, right? And again, this is a chart for two perpendicular surfaces, and the chart for the equation for the two disks. So the equation is really long, right? And here is two parallel plate. You know, here is the plate, the upper and the lower one, and this will give you Fij. And two plates with an angle between them. Here's Fij, and this is actually perpendicular surfaces. This is very important. So what are all those equations? Those are just physical geometry. It's really try to calculate the solid angle that one surface represents with respect to the other one. How much of that spherical dome does he occupy? If you occupy the whole thing, the solid angle would be 4 pi. And the view factor would be 1. If you occupy only half the dome, that solid angle will be 2 pi, and the view factor will be half, for example. Right? And for anything else, they are trying to calculate that fraction. All right? So, and all it takes is just you look at the picture and, well, what does he want? Wi and Wj, that's fine. Wi and Wj. And I will get Fij. And if I would like to get Fgi, I will just use the reciprocal rule. Okay?
A1 and A2, is that?
Let's write the equation first. So Mallory is asking, what is this area exactly that you're using when you're doing this reciprocal rule?
Surface area?
So that is the surface area that's radiating, right? So in something like this, you'll just basically assume unit depths, right? And this is three-side enclosure, F, I, J, and K, and he's calculating Fij. And this is important for boilers. When you have a surface, that's the flame and all those pipes that he's radiating to. So he would like to figure out basically I to the J, a row of cylinders, how much they will get from his radiation. And the charts. Okay, so as I said, those charts are not, sometimes they are not enough to get all the F in the problem. So you have to use this rule, reciprocal rule. There is also summation rule. The summation rule is simply that the fraction of my radiation going to every part that I see at the end of the day will end up being 1. 10% here, 20 here, 30 here, but at the end of the day, those all need to add to 1. So you will use this relation. If the table basically, or the chart, or the equation can give you 2 of them, then you can get the third. Right? You can get F11 and F12, but you cannot get F13. Then you can get F13 from this equation. Okay? It's called summation rule. And this is very useful too. It's called superposition rule. So, for example, there is a surface like this and surface like this. And you would like to calculate the heat transfer between them. So here is surface 1 and here is surface 2. And you're wondering what's F12. You open the tables or the charts or the equation, and all you can find is two perpendicular surfaces touching to each other. You never see anything where the other plate is lifted like this. So what do? You imagine there's a surface over here, and you call it 3. And you calculate F1 to that composite surface, 2, 3. That you can find, right? You can find from here. If this is 1, if you consider the base as 1, and the two of them together as this new surface called 2, 3, you can calculate F1 to 2, 3 from the chart. This chart or this equation here. You come here and you read like this. Alright? Here's one plate on the floor, one plate vertical. You can calculate F1 to this 2, 3. And then you come here and you say, well, that wall that I call 2, 3, I can split it into 2 and 3. Alright? And so obviously F1 to 2 to 3 is F1 to 2 plus F1 to 3. So once you get this from the chart, you can also get F1, 2, the imaginary 2, right? Or actually the imaginary 3 then. Let's call it the imaginary 3. So you can get F1, 3, right? That surface that you imagined, that's there. You can get it. How? Same thing. It's a little bit shorter. You come to this chart, and you can imagine that's basically it's a little bit smaller surface. And you can get his F1, 3. So now you have F1, 3 and you have F1 to 2 and 3. Then you can calculate this F1, 2. That was not really that clear from the chart. So now you managed to get F1, 2 from a surface, two surfaces perpendicular but not touching to each other. So this take a little bit of imagination. How can you split the surface, or you combine things to it so that it can resemble something that you actually have in your charts? Okay. Well, I have to admit, when I was an undergraduate student, that radiation was the hardest chapter for me in heat transfer course. Not because the equation is complex, but because of all those sea of charts and tables and equations that you use. But eventually, once you put your hand on the F, the equation just becomes J minus J divided by the R. Or if you take it even from the E to the E black body 1 minus E black body 2 over the F resistance and the surface resistance. And that's it. So the hard part is to come up with those F. Right? Especially when it has to do, especially when you have to use all those rules and not simply the charts. Okay, the fourth rule is the symmetry rule, and that is, if all the geometry are exactly the same, they will probably get the same shear. So F1, 2 is probably the same as F1, 5, the same as F1, 4, the same as F1, 3. Right? And it's how much? How much is F12 plus, how much is F12 or F15, or how much are all those guys? Brandon saying 1. Anyone have a different answer? F12 is the same as F15, is the same as F14, is the same as F13, equal to, for a free homework on Tuesday, on Wednesday, you have a homework on Tuesday that's due with a project. So that will be very handy if you have a free homework right now. 0.25. Excellent. What's your name? Robert got a free homework. Why, Robert? Why it's 0.25? They are all equal to 1, and the summation rule. So it's the symmetry rule that say they are all the same, because why would any one of them get more? And on top of that, Robert used the summation rule, which say F11 plus F12 plus F13 plus F14 plus F15 must be 1. Right? The radiation leaving 1 to everyone need to be 1 at the end of the day. And on top of that, he used the fact that F11 is because he cannot see itself. And so he realized that all those guys are 0.25. And he got a free homework. Alright? Very good. So now another consequence of that symmetry rule is actually 2 and 3 and 4 and 5. Why do we have to treat them as one body? Sorry, a different body. We can actually combine them and call them one surface. Right? We can just think the problem is between a surface 1 and another surface on top of it that's called, I don't know, surface B. Surface 6, let's call it 6. This case, of course, F16 is equal 1, excellent. F16 is equal to 1. All the radiation leaving 1 will go to the surface that's enclosing it, which is F6. Alright? And in a problem like this, you don't have solve 2 and 3. You can just basically say 2 and 3 are one surface. I'm just going to call it 2. So 2 can actually be 2 parts? Yes, 2 and 2. This is part of surface 2. Alright? And here is when those two surfaces are infinitely long. So those are two infinite long. So the depth is infinite. They go forever. You actually don't need a table to calculate F12. There is actually a formula for it. And it's, as you see here, I'm not going to read it for you. Alright? But it's basically the diagonal lines, 5 and 6, and 3 and 4, the perpendicular line. Alright? And L1. You can calculate F12 from this formula. Alright? So now let's solve an example and then I'll give you a quiz. So that the example will actually help you to prepare for the quiz. So the example basically say that there is a long furnace. So long, it go to infinity. Very long. So we are solving really 2D problem then. Okay? Because it's infinitely long. So assume unit depths, kind of. And it's 3 meter by 3 meter. Alright? And the top is sitting at 1400 Kelvin. And the wall is 1700 Kelvin. The two walls is exactly at 1700 Kelvin. And the floor is 600 Kelvin.
Is it the inner or the outer?
So those are all the inner. So and so the furnace is, I guess, electrically heated or something. And then there is this thick layer of insulation that's supposed to keep the heat inside. And so in that furnace, we actually have one like this in still water. And they actually last maybe 2 years ago. They were heating a certain material in, and there was an explosion from that small furnace. The floor, the people on the second floor, they were shaken by that explosion. That's how strong it was. So they were heating, it was like a certain polymer material or something. I'm not a material guy, but there was this material that when they end up heating it, it caused this. But what I'm saying is that you can really keep the inside very, very hot compared to the outside. Right? Okay, so, and he said all surfaces, so given, all surfaces, wall, ceiling, floor, everything have epsilon equal 0.5. All right? And he's saying that he's basically, he would like to calculate how much is heat radiation coming to the workflow. So that's why that's where he put his pieces. You know, if you have a piece that you're trying to heat or something, you put it on the floor. So required Q dot 1 over area 1. So let's call this floor 1, and let's call the ceiling 3, and the wall, I could make them 2 and 4, but that makes the problem very hard, and there is no need to call them 2 and 4. Let's call them 2 and 2. So surface 2 is basically 2 parts, part to the right and part to the left, because of the symmetry, right? That's why we can do this. So required is Q dot 1 over area 1. So he would like to find, so this would be in kilowatt per meter square. So to solve this problem, and that's the same for conduction and convection, you need to make this electric resistance equivalent to the problem to make your life easier. So basically you need to say, well, here's my surface 1, and he's going to be sitting at EB1, and then there is the resistance to radiation, the surface resistance to radiation 1 minus epsilon 1 over area 1 epsilon 1, and then you will have his J1. And here is surface 2, EB2, and he got his J2, and between them there is the resistance of the surface to the radiation, y minus epsilon 2 over area 2 epsilon 2. And then there is J3 and AB3. And what's between them is 1 minus epsilon 3 over area 3 epsilon 3. All right? So epsilon 1 is the same as epsilon 2 is the same as epsilon 3. All the epsilon is 0.5. Okay? And so 1 minus 0.5 is 0.5 divided by 0.5. That's another 0.5. So basically, we can just basically say it's 1 over area 1 and 1 over area 3 and 1 over area 2, right? All those guys will just cancel to be 1 over area 2, 1 over area 3, 1 over area 1. That is the surface resistance. Right? So J1 and J2 and J3, that's how much is the radiosity of each surface. That's what they are sending to the outside world. And what's between them? What's between J1 and J2? A resistance equal to, what is the resistance between J1 and J2? Does anyone remember? The geometry resistance. 1 over area 1 F1 2, or I can write it 1 over area 2 F2 1. Same thing. And here I will make it 1 over 1 over area 1, sorry, 1 over area 2 F2 3, and here 1 over area 1 F1 3. Does this make sense? So what do we want? He would like to find out how much Q dot 1, how much radiation is going to surface 1 or to the floor. So there is radiation coming like this, and there is radiation coming like this, and I don't know which direction, but I'm just making arrows. The equation will tell me exactly what direction. But every surface is radiating to the other guy, right? So there are 3 flow here, between 2 and 1, between 2 and 3, and between 3 and 1. And so that 2 to 3 could actually be 2 into 1. Well, chances are yes, 2 is actually radiating to 3, because 2 is high. But we'll see, because it has to do with this and this. We'll figure it out. But at the end of the day, the Q dot 1, where is it? Can anyone tell me where is the Q dot 1 can be drawn in this graph? Q dot 1 would be here, right? This would be Q dot 1. So eventually we are going to say, once we solve for, that is the solution backward. So Q dot 1 would be AB1 minus J1. So actually I'm plotting it in the other direction. Over R1, R surface 1. This is R1. Okay, of course it will end up being negative because we know that 1 will actually get the heat from the hotter guy. So, but when you write it like this, it will end up being 7.34 minus 1.66 over 1 over area 1. But actually I require Q dot 1 over area 1. So right, so actually we need it over here. So Q dot 1 over area 1 will end up being minus 159 kilowatt per meter square.
All of these R's,
We-
they're all radiation. Why are some of them, why are they the different ones? 1 over AF12, and why is it 1 minus F11, A1E?
So if the question is this geometry resistance, they are all the same value or not?
No, how do you know which R to use? What's the question of R to use?
Right, so this R1, I meant by it R surface 1. Or basically, let me take this out. It's 1 minus epsilon 1 over area 1 epsilon 1. So this equation is just for this one.
And what is that? That's the surface?
That's the surface resistance. So that's his black body radiation, that's sigma T to the power 4. And that's G1 that we will have to solve for it in order to get this.
How much is it absorbing?
So, just like in induction, the Q is the T divided by the R. In radiation, the heat transfer is the radiosity minus the black body radiation divided by the surface radiation, the surface resistance. So this is what he would have radiated if he was a black body. He's not. He's actually sending this to the outside, J1. The difference between this and this divided by the resistance is the actual Q. Alright? So it's hard to measure because I cannot point to a place in the surface and tell you, see, this would be that hot. Here's the temperature at that place. This J is not something that I can touch with the surface. The surface is actually sitting at T1. So that EP sigma T to the power.
Is at T1.
Right, this is sigma T1 to power 4. And this guy, we will have to solve for it. We don't really know it yet. I will have to ask you how we are going to solve for this J1. But this would have been the radiation per meter squared that would have leave him if he was a black body. He's not. He's having a smaller number because of this.
And what is our sigma?
And sigma, that's the Stephen-Boltzmann constant. That's the standard, it's 5.67. Right, that's the Stephen-Boltzmann constant. All right? So this is the plan for the solution. So now, in order to actually do this, we need to get all the resistance, we need to get all the J's. All right? So let's try to do this. So E black 3, that's simply sigma T how much is it? T3 to power 4, and that number is 217 kilowatt per meter square. All right? And then this is EB2, and it's sigma T2 to the power 4, and it's 473 kilowatt per meter square. And then this is EB1 and it is 7.3 kilowatt per meter square. So now you look at number 7, 400, 200, so it's obviously that 2 is really driving 3 and 1, right? So you don't have to know actually which one is driving which one. You can just assume Q dot 1 is like this, Q dot 3 is like this, Q dot 2 is like this, and let the equation give you the number. If you assume the wrong direction, obviously this is the wrong direction because Q1 will not send heat to this fire, right? 1 is the lowest temperature. I bet the radiation will be coming to 1 because he is at lower temperature, right? But I can just assume it like this, and from the equation it will end up being complete as minus 159. So I know it was in the other direction. Right, what are those nodes? Those are the J's. Okay? So this is J2, J1, J3. So to calculate my J's, I need to figure out the resistance in front of them. Okay, we already decided that the resistance here is 1 over area 3. That's the surface resistance. 1 over area 2, 1 over area 1. So how about those guys? I need those resistance to get the J's. How? If I manage to give you the resistance, how you can use this to calculate the J's? If I give you this resistance, this one, and this one, how can you calculate the 3 J's? So J3 minus J2 over R will be equal to what exactly? Well, part of it will be Q2, but part of it will be this. So it's really like electric resistance. We used to say that the current will split, and at every node, the current coming will have to be this much plus this much, right? If there is 10 ampere coming here, they will split 6 and 4 or 5 and 5, but they will split. Right? So if we get the resistance, so I'm solving the problem backward again. So I in the previous page I told you why I need my J, because eventually separating this part, the Q would be this minus this, E plaque minus J1 over the resistance. That's why I need my J. So now to get the J's, we are going to just use at each node the fact that the Q, the heat transfer, will have to split. The Q leaving surface 1 will have to go part to surface 2 and part to surface 3. Right? So here is the radiation leaving 1, EB1 minus J1 over R1. This will have to split into J1 minus J2 divided by 1 over area 1 F12 plus J1 minus J3 divided by 1 over area 1 F13. EB2 minus J2 over R2, that's the radiation leaving surface 2, equal to J2 minus J1 over 1 over area 1 F12 plus J2 minus J3 over 1 over area 2 F23. And finally, EB3 minus J3 over R3, that's the radiation leaving surface 3. What will happen to it? What will happen to the radiation leaving 3? Go this way and that way, right? Whatever Q is leaving here will go here and here. So here, that Q is how much? How much is that Q? Anyone? The Q here? J3 minus over 1 over the resistance, area 1 F13. And this Q will be J3 minus J2 over that resistance. Okay? So this would be J3 minus J1 over 1 over area 1 F13 plus J3 minus J2 over 1 over area 2 F23. Those are three equations in how many unknowns? 3. J1, J2, and J3. Assuming, of course, you know all the F. And you should be able to get all the F from the charts in the table. But if, so you solve, this is, by the way, the hardest problem in the competition. When you have 3 bodies. Hardest on your head, but of course, on a computer, piece of cake, right? You can solve many more on computers. So now the next step, or actually in real scenario, you will actually be solving it first, which is to get the F, right? So you have to basically figure out what is, right, so here is 2 and 2, and this is 3 and this is 1. So of course F22 is not 0, but F11 is 0 and F13 is 0. Right? And so we can get F12 easily because that's what the table are for. Right? You will find this F12, and you can get also F13. Piece of cake also from the table. 2 plates next to each other, you will find this.
Why is 1, 3, 0?
I'm sorry, I meant F33. I'm sorry. F33 is 0 and F11 is 0 because 3 cannot see itself and 1 cannot see itself, but 2 can see itself. Alright? And also notice that F12 is the same as F32. Why? Symmetry. F12 is the same as F32. 1 and 3, I mean, if it wasn't that they have different temperature, I would have called both of them 1 actually. But no, they have different temperature, so I couldn't call them 1. But geometry-wise, they are identical. Right? Geometry-wise, they are identical. All right, so I leave this for you. And then you get J1, 166 kilowatt per meter square, and J2, 376 kilowatt per meter square, and J3, 254 kilowatt per meter square. Alright, and once you get the G's, then you can solve those 3 equations, 3 unknown, and then you have your Q. Alright?